Binomial probability example. So there's 20 microprocessor chips in stock in this example. 3 have etching errors that cannot be detected by the naked eye. 5 chips are selected and installed in field equipment. So in part A, they want you to find the PMF, basically your probability distribution of X, the number of chips that have etching errors. So X being the random variable, and we're looking at 5 chips being selected, and some of them might have errors, some might not have errors. So there's really 2 choices there when you're picking a chip. It's either got an error or it doesn't. And whenever you have that scenario where you're picking out of a group, so many might have the success, in this case the error, or the failure, not an error. Kind of weird, but in this binomial model, successes aren't always good. You're just saying, yes, I successfully picked one with this trait, whether that trait was good or bad. And here, in a sense, it's bad. You're getting an etching error, which means the chip isn't good. So whenever we have that scenario where it's like good or bad, or success or failure, when you're picking things, you're looking at this binomial. Bi, the prefix, stands for 2. So 2 choices, binomial probability is what we're going to use. So I know overall then that the probability of X equaling X is going to be using this probability model of N choose X times P to the X power. So the P will be the probability of success, and then Q will be N minus X power. And notice that the powers, X and N minus X, when you add them together, you get the total of N. So for example, if you're looking of selecting, in this case, the 5 chips, where N is now going to be 5, the total selected is always your N. And out of those 5 chips, maybe we want to see if there's 2 that have an error, that successfully have the error. So your X would be 2, and then you would have the power of 2 for the probability of success, which makes sense. You're saying that there's 2 of those. And then the Q, the probability of failure, you would have 5 minus 2, or 3 of those. So that's how those powers always work. They should add together to be to N, and the probability of success will have the power representing how many you're hoping to successfully choose, and the probability of failure will have the power that is the rest, so to speak. So the N choose X, why do they use this? Well, let's get down into an example, and I'll show you why that is coming into play with that N choose X, that combination idea. So for part A, I'm going to set this up with a little x here, probability of X equals X over here. And we could have 0 defects. Remember, we're choosing 5. We could have 1 defect. We could have 2 defects. We could have 3 defects. We could have 4, or we could have 5. Now, in this case, they say that only 3 have etching errors. And you might be asking, well, why about the 4 and the 5? Isn't that going to be an impossible case? And from what I understand in going through everything I've gone through, and even talking to some people about this, you don't worry about the impossible cases. The probabilities in the binomial model will handle that for you and essentially make the 4 and the 5 so small that they're negligible anyway. So we won't worry about that fact that there aren't 4 or 5 in the batch. And it's kind of weird to think about that way, but I've been assured that the impossible cases you don't worry about with probability with the binomial model. So let's take a look at the 0. So for 0, that means I'm selecting no etching errors. And if we use this S for success, which is actually an etching error, so I'm going to go ahead and just put that in instead. It's weird again that an error is successful, but that is the trait they're successfully trying to select. And then a failure is no error. So what you'll have here then, for the 0 case, when X equals 0, you basically could have just F, 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 and F. You don't want any with an error when x is 0. There's only one way for that ordering of f's to happen. And, or really one way to choose none out of the 5 that have errors. They're all going to be f's. So this one isn't as illustrative of the n choose x, but if we were to put this together and say, okay, probability x equals 0 is going to be, in this case, the n is 5, 0 will be x, and then we need a probability of success. And this is where the other pieces of information come into play. There's 3 that have etching errors out of the 20. So in this case, the probability of success, the p, will be 3 out of 20. And then the q, the probability of failure, is just the other side of that story. So that'd be the 17 out of 20. So we'll have 3 out of 20 raised to the 0 power. We don't want any of those. And then 17 out of 20, we want all 5 of these. And when you work this out, what you get, and I'm going to go ahead and move this over a little bit here, is 0.4437. So going out 4 decimal places, you get 0.4437. So that'll go right here, so 0.4437. All right, so then for the x is 1, and I'm actually going to back this up a little and do it this way. So when f is 1, or x is 1, sorry, that means that you have 1 success in those 5 choices. Well, one way that you could do it, maybe the first one you picked got off to a bad start. It was successfully an etching error, and then the rest are failures. That'd be one possible outcome. Well, another possible outcome would be a failure first, so no error, and then success, then failure, failure, failure. And another one could be that you got 2 failures, then a success, then a failure, then a failure. Another one could be failure, 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 so all good ones, and then you successfully picked a bad one, and then a failure. And then last but not least, you could have all of the first 4 you picked being no error chips, and then you successfully pick one with an error. So looking at this expanded, you see that there's 5 possibilities when you are picking 5 chips and looking for there to be one bad one in that mix. And this is what the 5 choose 1 will do for us in this probability x equals 1 formula. So this 5 choose 1, which is in your calculator, just to write this down here, the 5 choose x in general is you're using the 5CX or the NCR button in the calculator. So if you're looking on your calculator, you may have to go to the probability area of it, the PRB area, or some other mode, depending on what calculator you're using. But the NCR is what comes in. And if you go to desmos.com, which is a website that's great for doing these math calculations, you would put C with the NR in order in that way to figure it out. So a couple of different ways to approach it. But if x equals 1, then you're going to have 5 choose 1, and then you'll have the probability of success to the first power, and then the probability of failure to the 4th power. And when you work that out, you get 0.3915. Okay, so 0.3915. And I'm going to go ahead and just kind of work through the rest and get those values. And in getting those values over here on the right, you're just continually filling in the formula by increasing the value of the x. And you can see then in filling in the table, you get to the 4 and the 5. Those probabilities are so small, not really an issue. And again, I've been assured that you don't worry about the impossible case here. So even though there aren't 4, the probabilities here are pretty small, not going to happen. Okay, so that satisfies the part A. And then in part B, the expected value of x, the e of x, the variance of x. Since this is a binomial model, what they have given us, then the n times p is just your expected value of successfully picking an etching error, the number that you would expect to see. And in this case, the n is 5. The probability is 3 out of 20. So you get 15 out of 20. And that reduces down to 3 over 4, or 0.75. So you expect to get, on average, when you select 5, and you do this many times, you're expecting to get less than 1 on average. That would be, the errored chip. So for the variance of x, again, binomial has a special formula. It's NPQ. So we have 5 times 3 over 20 times 17 over 20. And the variance ends up being 0.6375. I'll go ahead and put all 5 or 4 of those there. And if you take the square root of that, that would be your standard deviation, or the average amount of difference, if you did this many times, between the mean and all the different values that you might see in your random set of trials, selecting 5 over and over again. All right, so then in part C, we start getting down into ones that actually want you to find the probability. So probability that no chips with etching errors will be selected. Well, we already got that in our little table here. This is the great thing about doing the table first. So probability that x equals 0, the random variable equals 0. It's going to be just 0.4437. So all that work we did earlier is paying off. And that would be the answer. And then in part D, find the probability at least 1 chip with an etching error will be selected. So at least 1 chip with an etching error means that we got to think of 1, 2, 3, 4, and 5. And again, with this, the 4 and 5 are impossible, but the probabilities are so small, we'll leave that out of there. Now, if your instructor is actually accounting for the impossibility of 4 and 5, then you would not add the 0.0022, the 0.001 to this. You would just put in 0 and 0. But from what I've been told, you just put them all together, and because they're so small, it's negligible. So what we're going to do then, again, is we're going to add together 1 plus the probability of 2, 3, 4, and 5. And just pausing there to kind of write this out, where you're just adding together the technically 5 probabilities that handle the cases 1 through 5, at least 1, then you get 0.5564. So basically what you're seeing here is there's roughly a 44% chance that you will get no errored chips, and there's roughly a 56% chance that you will get at least 1 chip with an error when you're picking 5 out of the batch, with this probability of 3 over 20 to get a errored chip. Okay, I hope that helps you with binomial probability, and thank you for watching.